I'm starting a presentation now. So this is the project title for my presentation and a real quick background about myself. I'm a junior CSC student at Amrita University from India. My area of interest lies in the field of computer vision and machine learning. Actually, I took an academic elective last year on digital image processing, and that's how the interest developed. And I'm being mentored by Dr. Badley Alicia, as all of you know, is a senior contributor for OpenWorm. I'll speak more about the OpenWorm Foundation and the DevoWorm group in the coming slides. So I think we can move to the slide 2. So these are the topics that I'll be covering in this presentation. First, I'll be giving some introduction to the project, and then I'll take you guys on a walkthrough with my proposal so that you can understand what is my approach to the problem, and what are the things that I have done during the community bonding period, and what will be the end products of this after the 3 months after GSoC, and the tech stack that I will use, and I'll give some links to follow the progress of the project, and I'll be discussing the future scope of this project, like what can be developed after this stint. We can move to the next. So let me start with the OpenWorm Foundation. Its main aim is to create the first digital organism in a computer, and it has many subgroups like Gepetto, DevoWorm, Cybernetic, WormSim, NeuroML, as you can see. These are all the organizations to which OpenWorm is the like an umbrella organization, and each of these groups focuses on specific things. And this GSoC project belongs to DevoWorm group because DevoWorm basically focuses on the developmental dynamics of the worm of a nematode actually, like what all happens from the zygote to the adult cell, what things. Like how does the worm evolve over time. So this group will be focusing on that, and this GSoC project belongs to DevoWorm group, as I'll be dealing with embryogenesis process. And like I said, the aim of OpenWorm Foundation is to create the world's first digital organism. That is this nematode that you can see here. This is the C. elegans. It's a worm. It is roughly around 1 millimeter long and can survive up to 2 to 3 weeks. So why do we need to study about this worm? Because it has a simpler nervous system compared to rather complex systems like the human brain. For suppose it has around 302 cells in the nervous system and about a total 959 adult cells in the adult organism. So it's really small and simple compared to human, where the cells in the nervous system are almost 100 billion. And you can see this picture here. This is actually a simulation of the brain of the nematode, which is represented as a graph here. And I think one can learn more about C. elegans and other terminologies from Worm Atlas here. It's like the golden resource for beginners. And yeah, moving forward. So yeah, the main idea behind studying this worms, how the worm functions, is to apply the principles that we have learned to the human brain so that we can correlate how the functions happen inside the brain. And so it is believed to be the first step that need to be taken to understand the human brain completely. So that's basically the aim of OpenWorm. And coming to the introduction for this GSoC project, so the primary aim is to provide plugins to ImageA tool for accurately segmenting the cells of C. elegans during its embryogenesis process. Here's a small video for you to get an idea of how embryogenesis might look. So I need to develop plugins to ImageA, which can segment the cells when the process is happening right here. And to tell more a bit about ImageA, it's an open source image processing tool which is widely used in the open science community around the globe. It's really famous for scientific image processing and stuff like that. So I'll be developing plugins for that tool. So instead of this bright field imagery that you could see, there's another type of imagery. There are actually many types, but I chose to stick with spin images. Here's a sample spin image of the embryo that you can see here. It makes things a lot simpler in my opinion. So I'm going with this. You can learn more about spin images like and how they're captured and all from a simple Google search or the link that you can see here. And sorry, a quick check. Am I going too fast or something like that?
No, I think it's fine. Just keep going.
Yeah, thanks. And we need to discuss about the previous work on this problem. This same task was solved in GSoC 2017. Then the student added classical techniques for for solving the same problem. These are all the classical techniques that the classical image processing techniques that were added. Out of this lot, the level set algorithms were the best. That gave the best results of these things. You can find the code in this link that you can see below. The code is available on GSoC 2017. And the question is, why do we have to focus on this again? Because we're not really because these algorithms that you can see here, they depend on the local features of the image. So for suppose if you increase or decrease the brightness or contrast levels of the input image, then you can expect the result to vary drastically because the classical techniques cannot adapt to that change. So I am proposing deep learning based approaches for solving the project, for solving the problem. And I want to take you guys on a quick tour on my proposal right now, so that I can explain my approach. So the project is divided into two parts: the semantic image segmentation part and the automatic feature analysis part. This I'll come later. And again, in the semantic image segmentation, I have two approaches. One is the semi-supervised approach and other is the unsupervised approach. And the question is, why can't supervised approach work? Because we don't have any labeled data for supervised algorithms to work on. So I had to propose these two techniques. And each of these techniques has a backup task in case I have a problem with implementing the primary task. That's again the idea of my mentor. He suggested me that. And here's an example of why the classical images might fail. This is the input spin image, and I applied a mean shift clustering algorithm here. Here you can see the clusters. When I slightly changed the brightness levels of this input image, it resulted in this image. Here you can see some edges got faded away. So that is the problem actually, and we can solve this by using deep learning methods, as they can adapt to such changes from if we can include such examples in the training data set. And the semi-supervised approach. Okay, and for the semi-supervised approach to take part, we need at least we need some labeled data available so that we can do the semi-supervised algorithm. We can use our semi-supervised algorithms, but there's no labeled data. So for that, initially, I thought of a new method that I thought will be useful for us. Here's a spin image that you can see. I hand annotated this, image, and I thought, what if we could generate images which look similar to this? Like it's by intuition that we can say that the embryo looks like a kind of ellipse kind of shape, and the shape is a bit unstructured, and it has structures like this inside. And so, if we can get the logic right to replicate this patterns if we can synthesize the images, I think from these synthesized images to images looking, we can convert these synthesized images to spin images by replacing the colors. Actually, of course, there need to be a randomness sprinkled in there, like the green color can be replaced with black with white gradient, and the white and the yellow color can be replaced with white gradient, and so on, like that. So once we get this is not a perfect method, but for generating some labels, I'm doing this. Once I get some data set, I'll apply image augmentation so that the data set will have more variability. And then I plan to use GANs, which are famous in semi-supervised trainings, and also use variational autoencoders as a backup task in case I'm having some difficulty with GANs. Even this does the same thing as what GANs do here. So that's basically the semi-supervised approach. Now coming to the unsupervised approach, there's a deep learning model called a WNet, which can do for image segmentation with fully unsupervised approach. So we don't need any kind of or of labels of labels for the input images. So we can just plug in our data set into this deep learning model, and we can apply some post processing methods like CRF smoothing and hierarchical segmentation, so that we'll get state of the art image segmentations as a result. So this is the primary task for unsupervised approach, and I also have a backup task for that in case we are not really satisfied with the results what WNet has produced. There's some other approaches that I found on the net, and that's called unsupervised segmentation by back propagation. And that's that. It actually depends upon if there's a certain key points of an image. If for every key point there's a descriptor assigned to it, and the clustering takes base is done whether the descriptors of the key points are similar or not. So the same key point, the same descriptors will be put into one cluster. So that's rule number one for this thing. And the spatiality continuous pixels tend to be clustered into one. That's obviously that sounds obvious because we need objects. The objects are always connected. So that's about the unsupervised approach. Now coming to these are some pros and cons. You can read my proposal. I'll be hosting it on my Tumblr blog. And then this is the automated feature analysis. Initially, we did not really work on this, like what might be a good thing to do. And then yesterday we had a discussion. Me and Bradley sir had a discussion of what might be a good thing to do, and I arrived at a task to solve. Basically, we'll be getting some. We'll be having bright field images or like this, bright field movies like this, of the embryo splitting and eventually evolving as a worm. So if we can track and tag these cells, I think that might be a good thing to do. And I've found approaches also, approaches also for that task, like this that you can see. There are so many. There's so much much research that has been done in this field, so I can take all that information and try to code up a customized plugin for this task. And of course, we'll proceed on this if it sounds good to my mentor, and we'll have to work on this part a little bit more. So that's with my this is the timeline, and yeah, that's with my proposal. Now I think we can get back to the presentation. So I want to highlight some points what I have done during the community bonding period. I've set up the development environment, like I've installed some IDEs, practices the workflow for developing plugins and etc. And participated in the weekly hackathons, like the one that we're doing in right now. We've discussed and created and solved issues for the project. I ran into some trouble with Python programming. Basically, I wanted to try Python code within the Java code for through which I'll be writing the plugins. So I found out Python to be ineffective for my task here, and I did some research and I chose deep learning for J framework, which enables us to directly implement deep learning models inside with Java itself. And my mentor gave me some GSoC reading materials, which are very helpful. I've been going through them every now and then. Basically, that's what I've done majorly during the community learning period. And the medium of deliverables. So the end products will be the unsupervised DL model for segmentation. It will be served as a plugin to ImageA, the same for semi-supervised DL model. And the third thing is the tagging and tracking of cells from bright field images. This needs a bit work to do. And this is the tech stack that I'll be using. All these three frameworks, these two are for Python and this is for Java. I'll be using these technologies to develop the deep learning architectures, and through this I can write the Java code through which the plugins are written, and I can plug them into ImageA here. So that is the open source tool where all the code ultimately reaches. So where do we follow this project is that all the code for this GSoC period will be uploaded here. All the micro reports, like the weekly micro reports, what all the progress of the week and the next week will be written here on the Neurostars page, GSoC 2019. This of course is only visible to it's a closed group, I guess. So I'm maintaining a Tumblr blog where I'll be detailing all the things that I've done in the week. And of course, these YouTube, these hackathon discussion, these weekly discussions will be uploaded in the YouTube channel for DevoWorm. There we can revisit all the discussions and the future scope of this project. So last week I came across an article where Google released an dataset called Open Images version 5. It has around 2.6 million objects, segmentation marks for 2.6 million objects. I wondered how they could create segmentation masks for such a large number of objects. Then I've read the blog, and they stated that they initially used an segmentation neural network, and from the of course any deep learning model will have some error in it. So to solve that, to minimize that error, they have taken the output from the neural network, and they gave it to the human annotators who iteratively corrected that segmentation, so that so finally there's a data set completely available. There is a data set for image label pairs. There's an image, there's a accurate label for that. So with this process, a new data set will be created, and it also will be huge in size. With that newly formed data, they'll train a new deep learning model, and that will eventually result in state of the art. So that's the process of what Google is trying now. So I think that can be applied to this project as well. Like I'll be developing some deep learning models right now in this GSoC period. Of course, they'll have some error. So for that we can ask people or new contributors to the community. We can ask them if they're interested in correcting the errors so that the data set will be increased. So I think basically that is what I think about the future of this project. And finally, any questions?